Okay, hi, hello. Section 10, the last one. My little heart, I can't take it. Thank you for coming today. Yesterday was a lot, I know. Sorry the exam was tough. It was a tough exam. Particularly, I think that the box problems were harder. Like, the box problems were definitely the hardest part of the exam. And so, with that at the beginning, that throws off the timing for everything else as well. Like, we should have probably given you, like, a heads up of, like, hey, don't get too bogged down. The mechanisms I thought were a little bit easier than some of the practice exams, and then the synthesis I thought were about the same. And honestly, I'm not super pleased with the exam. Like, I feel like we could have done better. It was my first time writing exam 2. I wrote like 70% of it. And yeah, I think I just went a little bit too hard with it. There were some questions that I just think also were kind of bad. Like one of the box problems on the first page that had NaH on it. Let me see. Yeah, this is the document that I sent to Logan with a draft of the exam. So this one, with the NaH, the thing that's weird about it is once you deprotonate this O, make it O minus, for SN2, like we want you to do an SN2 intramolecular attack, but for SN2, this is secondary, so it's fair, and then for E2, we have an O minus, so it's good, and so like you could do an intramolecular E2, which is just weird and not what we wanted, and we'll give you full points, but we're going to try to give credit where we can. But yeah, I think part of it was I wrote hard problems, and then Logan tried to make some of them easier, and some of the edits made them more confusing. And so, bless you. Yeah, these are kind of what I sent Logan. And most of the things that I wrote made it in. One of my syntheses did not. What else? Lots of allergies. There was someone who like sneezed like 30 times in the 8:30 a.m. section. Yeah, I support you, girl. Cowabunga, dude. But sorry, I'm really trying to make Cowabunga work. I'm trying to bring it back. But yeah, what I said earlier to those of you that were in here, final exam is not going to be harder. It's going to be more of exam 2. And then we add on some lecture 10 questions for mechanisms, and we add on some of the questions that you were good at from exam 1. And so typically the final exam score is higher than exam 2, whatever it is. Logan was very kind because I'm going to be going out of town this weekend. I'm going to the Williamstown Theater Festival. I'm going to see 7 shows over the weekend, which will be fun. Yes, so I leave right after this, and I was going to be like grading y'all's exams in between shows, and Logan was like, how about this? I'll make you a deal. I'll grade, Logan was saying this, I'll grade the entirety of exam 2 if you grade all the final exam. I said, bet. Because I think he's going to a conference next weekend, so it just works out well for us. And Logan is also like, I want to try to get it graded as fast as possible so they get feedback and can use that for studying for the exam. So I wouldn't be surprised if you got scores back on Saturday or Sunday. So we're, again, trying to do a real fast turnaround there. And then also, historically, what we do is we will post your final exam score as well as your course grade when we know it. So you won't have to wait for Harvard to release it to you. So you'll kind of get that information as soon as we have decided at the very end. But that's kind of the course logistics. Next week, we have normal help room on Monday, and then it looks like we're going to have help room on Tuesday and Wednesday. We were debating, like I'd been kind of polling the other sections before y'all of would you rather have just more Tuesday help room and no Wednesday, or sometimes on Tuesday, some on Wednesday. No one's been coming to the Wednesday help room. Like fewer than 5 people come to the Wednesday help rooms the day before the exam, and so we're like, maybe people just are busy. Maybe they don't need us. But no. No, love a busy help room. Come by even and just like study, like chill. Yeah. But so we're probably going to do Tuesday and Wednesday help room. And then we have the 2 paper practice exams. We're going to try to also release a 3rd one digitally next week, probably on like Tuesday. And then also we are going to go and release extra exam 1 and exam 2s from past years. So you have practice exams C and D for exam 1 and exam 2. And really, like, practice is going to be the biggest thing getting you to and through the final at this point. But that's most all I have in terms of announcements. Yeah. Then you're probably not going to have it on the final. Yes. Yeah. And again, if I see a draft of it and see otherwise, I'll let you know. But yeah. Yeah, Radicals, love her. Love her. So, game plan. Game plan for today. We are going to go through lecture 10, and my goal is to have more than half of the challenge problems on the P-set done so that you can take a little bit more of a rest break this weekend. So we're going to try to be very challenge problem heavy. Yes, any other logistics questions before we jump into section proper? What a great turnout for the last section. Oh my gosh. Ding dong. I'm excited. Okay. Also, the soundboard is wild for today. So for my first transition, I give you...
This is my meal. I call this girl dinner. Girl dinner. Girl dinner. Girl dinner.
My girl dinner is Enolate Chemistry. And soon it will be your girl dinner as well. So to help guide us in Lecture 10, because Lecture 10 can feel a little bit spread out, a little messy, I've really tried to narrow down the scope of it to 6 of the key big ideas or facts to guide us. So that's going to kind of ground our discussion today. So first up, our first big idea is hydrogens on alpha carbons are acidic. So normally, hydrogens on carbon in like an alkane, we know our pK is about 50. But what we see is the pKa of most carbonyl compounds is around 20. And so let's look at why that happens. Well, if we deprotonate with a base at the alpha position, and alpha is just to the left or right of the carbonyl, then the electrons can fold up into the O of the carbonyl. And what we get is this enolate that has resonance. So this enolate spreads out the negative charge over 3 atoms versus just an alkane where you have a negative charge on a carbon, which that's what's not super stable. Now, in order for this to happen, we do have a molecular orbital requirement, kind of like how for E2 we had the anti-periplanar beta hydrogen. For enolate formation, we need the sigma CH of the hydrogen that we are going to deprotonate to be exactly parallel with the pi star CO of the carbonyl. And typically speaking, like when we have just a free carbonyl that's not on a ring, it's going to be able to rotate freely. That won't be an issue. And to be so honest, we're not really going to ask you much about this except for one challenge problem, which we're going to do together to talk about it a little bit. But this type of MO requirement is something that's going to come back a lot in 27, where you need these like orbitals to be lined up in certain ways for a reaction to happen. So I want you to be kind of used to thinking about that as like a criterion. So alpha hydrogens are acidic. And our second big idea is once we make enolates, enolates are nucleophilic at the alpha carbon. So we can push in, and then this double bond can go and attack an electrophile, and it creates a bond between the alpha carbon and whatever the electrophile is. And especially if our electrophile has a carbon, which we know several carbon electrophiles now of carbonyls, of epoxides, of enones, like lots of carbon electrophiles, this is now a really powerful way of making carbon-carbon bonds. Whereas for exam 2, you only had like 4 ways that you can make carbon-carbon bonds. This really opens up the floodgates to a lot more options. So one note on this is just like we have the distinction between alcohols and alkoxides, we have a distinction here between enolates and enols. So the ATE ending here is for if it's negatively charged, but if you have a neutral version of it, this is the enol. Now the enol, like alkene, alcohol, it is still a nucleophile. It can still push down and attack the alpha carbon, but because you don't have a negative charge on it, it's not as good of a nucleophile. So you'll use enolate in basic conditions, and then you'll use enols in acidic conditions. Speaking of acid and base, the enol is called a tautomer of the ketone. And really, that's just a fancy name for a structural isomer here. So they both have the exact same molecular formula, but if we move one of the hydrogens from this carbon over to the O, and then change where a double bond is. That's how we get from a ketone to an enol. And so this is an interconversion between these two forms that can happen really, really fast in a reaction mixture. So in acid, what's our typical first step in acid? We protonate. So we protonate the ketone. And now this is OH plus. It's making this even more acidic. And so a not good base like water can still come and deprotonate it and push up, and then we make an enol. So that's how it would happen in acid. And then base, typical first step is deprotonate. So you can deprotonate the alpha position, you make your enolate, and then you can neutralize it with an equivalent of water, and then you're at the enol. So this thinking in base and acid, you can do that for most of the reactions in lecture 10. We primarily will be working in base, but we'll see one or two examples where it's an acid, and we'll talk about that today. Cool. Yeah.
For what you said before, in like the enolates or nucleophilic at the alpha carbon, why is that new? Like we saw how like we can do alkene additions. Like what's different about this?
Alpha carbon to a carbonyl. That's the new thing. Like we're used to seeing carbonyl compounds react at the carbonyl itself, and the new thing is actually the position next to the carbonyl can be a nucleophile. Whereas typically we think of as carbonyls as just electrophiles, right? And so that's kind of the new idea. But with that, we can see enolates in a lot of different variants. And so it feels very like Super Smash Bros. Like, choose your fighter of the enolates. We have our aldehyde and ketone enolates. We have dicarbonyl enolates. We have ester enolates, and even weirder ones. It'll just keep on going unless I stop it. Anyway, so the ketone aldehyde ones, their pKs are around like 17 to 20. But then we see that when we have a dicarbonyl, it gets much more acidic. It's 11 to 13. So that's one thing to spot out for. If you have alpha hydrogens between two carbonyls, it's way more acidic. Now, if you had the choice to deprotonate this hydrogen, we could either fold in the electrons up and to the right, or we could do it up and to the left. And so how do we decide what to do when we have options? Well, look who already has electrons. So on the ester side, this is already getting electrons pushed into it from the OR group, right? So the side that's going to be more electron poor is going to be the ketone side. And so it would fold up this way. And that's why this is our main enolate that we form. The other thing is like comparing aldehyde and ketone. Well, remember our R group for a ketone, like just an alkyl group, that's going to be electron donating via hyperconjugation. And so if we were trying to fold in electrons here, there's already some donation happening from the R group, which is making it harder to form the enolate. And that's why aldehydes are more acidic than ketones here. We can even have weird ones like here, the CN nitrile. We can deprotonate the alpha position, push in, push up, and we get this weird looking thing, but it still can push down and go and attack an electrophile. Easy peasy. And a sneaky hidden enol equivalent that you've seen before is an enamine. Oh my gosh. So she can just push down and go and attack something. Crazy. So if we were to look at challenge problem 4b, what do we think is going to be our nucleophile? Is it the left molecule or the right molecule? The right, our enamine. So this is going to push down, and then the double bond's going to go and attack something. This is our nucleophile. So this molecule has to be our electrophile. What are our good acceptor orbitals on this electrophile? Pi star CO. What else? Sigma star CBr. So if we look at our product, which does it look like we attacked? The pi or the sigma? Yeah, the sigma star. So we are going to go and simply just do a backside attack. Okay. So then we get to pH, and my alpha carbon I'm going to put over here in red, and then I'll put the one it attacks in blue. And then on the other side, we should have hydrogen, and we pushed down and made a double bond to nitrogen. So we have a cute little aminium. Okay, well now it looks like to get from here to the product, we have an aminium going to an aldehyde. Have we seen that reaction before? Yeah.
Wasn't that
This is our lecture 5, amine hydrolysis. So you do need to write the mechanism on your actual PSET, but this is the kind of setup here to get it started. Work. So let's talk about another kind of theory thing with challenge problem 1, and we'll work it fully. So basically it gives you 2 molecules here. Each of these are like bridged rings, and we see one of them has a carbonyl and pK is around 20, and the other one has a carbonyl and the pK is around 40. If we have a carbonyl in the molecule, what do we expect the pKa to be with our alpha hydrogens? Around 20 or around 40?
Yeah, I don't think.
Around 20. So this is expected. This part is unexpected. So this is closer to an alkane. So let's try to see why that happens. Well, we said that when we're in the ring, it's harder to get that MO overlap that we need. And we need an overlap between the sigma CH and the pi star CO. So let's draw some of these orbitals. So our pi star CO is here for each of these. And then let's draw out all of our alpha hydrogens. So we have, I'll draw them in green. So I'm going to label these hydrogens 1, 2, and 3. Which do you think has a sigma CH bond that can overlap well with the pi star? Can you show me in your hands, like 1, 2, or 3? Which do you think will have good overlap with our pi star? Work. So, it's tricky to see. Here, when our pi star is going like this, then we need our sigma to kind of be, and again, I'm not drawing this on a molecule here, it needs to be lined up with either the top lobe or it needs to be lined up with the bottom lobe. And if we see that, the one that's actually lined up most with the bottom lobe is this one. And that's not super intuitive, right? But it's kind of like, imagine the pi is kind of like this, and then this hydrogen that's next door is like sideways to it when we need it to be parallel to it. It is like intersecting here, perpendicular to how we want it to be. We want it to line up directly like this, where it can slide easily across. And so that's why, even though 2 looks like it could have good overlap, this third one is the only one that really does the job.
It's perpendicular to that.
Yeah, so this, think about it this way. The bond is parallel with like where the sigma bond is, but we need it to line up with the pi star, which is going to be perpendicular to that. And so we actually do not have this sigma bond line up well with this pi star. They're going to be like, one's going sideways, one goes up and down. Yeah.
So does that mean like that highlighted green hydrogen, that goes well because it's perpendicular of that?
This one right here that's shaded in is the one that has good overlap because it's parallel. We want it to be parallel. We don't want it to be perpendicular. So what I'm going to do is I'm going to not draw the other hydrogens just to kind of make it clear which one's the important one. So this is where we have the good overlap. And so our base is going to come along, bloop, fold in, kick up. So the enolate that we get from this is this. And so this is kind of the normal enolate we would expect. If we had done it on the other side, what gives you pause about this structure? It violates Brett's rule. Who was Brett? Why does he have this rule? Couldn't tell you. Now with this one's also kind of hard to see, But imagine this pi bond is in the plane of the board. It's going kind of sideways like this. And this hydrogen is coming out of the page towards you. And this one's going away from you. Do you see how neither of these can line up with our thing that's in the page? Like if something's going out, it's going to be perpendicular. If something's going in, it's going to be perpendicular as well. So here we have no good sigma CH to pi star overlap. And moreover, if we tried to draw one that enolates from this, again, violates Brett's rule. So that's why, because we can't form a good enolate over here, that's why our pK is 40. It's like we're going to have a negative charge isolated on a carbon, which is really unfavorable, versus over here we can put the negative charge all the way on the O and do our normal enolate stuff. So with this kind of MO requirement, let's see in one more example with a chair. So here, let's draw our pi star. Whoop. Well, we have hydrogen 1 over here and hydrogen 2 over here. Which of these seems like it's going to overlap more parallel with our pi star, 1 or 2? 2. Great, great, great. So this sigma CH is fine and dandy. So our base is going to come along. It's going to fold in, kick up. What we get then is and then if we look at the product, well, the product looks just like what we had before, but we have replaced our hydrogen with a deuterium, and that's because we're in D2O. So that's just like deuterated water. Dude water. Water for dudes. I don't know. Cowabunga. So all we do, this is kind of a silly reaction, because all we did was deprotonated, made an enolate, and then reprotonated back to the carbonyl. But it shows the point that the product that we have only has a deuterium here and not at the other position. The other position is still a hydrogen. Because there's no overlap, we can't form the enolate. And that's challenge problem 1. So, any questions on our enolate basics here? Yeah. Yeah.
So on the concept, is it fine that I can draw it in like a planar shape? Draw like planar instead of like being in like a chair conformation? I can redraw it.
So just because you draw it planar doesn't mean that that's what the geometry is, you know? Like, the real geometry is going to look much more like a chair, and so we want to do what's reflective of the molecules.
I mean, like if I'm drawing like planar, then it would just like kind of like read more visually. Like I'm just saying, I'll be like, oh okay.
But when you draw it planar, the molecule isn't planar, you know? So, like, you're not able to adequately answer the question with, like, proper bond angles if you draw it planar. Like, for this, you have to draw it in 3D structures.
Because like on the practice exam, I noticed in like the product, the from chair conformation, it's like planar. So I was like,
That's for E2 on a ring, which we can do a little bit differently. But for this, trust me, just draw the 3D structure. So, with that, let's head on to our next big section. So, we have our first icon of the day. Say hello to this icon, the aldol reaction. Hey, icon. So, the aldol reaction, all it is enolates that attack a ketone or aldehyde. So a ketone or aldehyde is the electrophile for an enolate attack. So with this, we get a few different products. So one product that we can get, we have created an alpha-beta bond. So our enolate went, pushed down, attacked this carbon, And we see there's a new bond that's created between our alpha carbon of our enolate and now this beta carbon that used to be in the carbonyl. With this, the carbonyl that was on the electrophile is now an OH, an alcohol. And so this, the government name of it is a beta hydroxy carbonyl. But her preferred name is aldol here. So this is one of the new compound functional groups that you're going to want to scan for. And these new compound functional groups are really, really important to lecture 10 questions, especially in the final exam, because half of the challenge is just clocking what reaction happened. And so knowing that you have to be on the lookout for these kind of bigger functional groups, and you can't just be in isolated, well, that's a ketone, that's an alcohol mode. No, we need to be able to see this kind of connection too.
So more functional groups on one flashcard then.
Yes. So then our aldol could go and react even further and become an alpha beta unsaturated, and that's our biology word for a double bond, like unsaturated fats, an alpha beta unsaturated carbonyl, but you know her by a different name. How do you know her? Enone. So now we have a way of making enones full circle. We started with enones in lecture 3. So we call these two products our aldol addition product. So this is simply we've added it together. And then condensation here comes from the fact of our biology math of if we remove a hydrogen and an OH, we basically remove water. And so that's our aldol condensation product. Now, for the purposes of our class, we're mostly going to be showing this as mechanisms where we give you the product, so you'll be able to see, did it stop at the aldol or the enone. But some classes, like if you were trying to use it and you wanted to specify, they would write a delta to show that we would heat it in order to get more of the condensation product rather than aldol. We are not that picky with it. So our mechanism here, we first form the enolate. The enolate attacks the carbonyl like we've seen before. And then, once we do that, we've made carbon-carbon bonds. Do we have any leaving groups on this blue atom? Oh, no. So our R2 is another carbon, and it's harder to break carbon-carbon bonds. So we don't really have anything that we can kick off easily. So all that we do is we protonate it, and that's how we get to our aldol addition product. Then, once we are here, we are still in base. We still have alpha hydrogens. So we could deprotonate it one more time. We have made an enolate, and then we do what Logan was calling the super lone pair push, which he tried to call it deluxe, which to me this does not give luxury. It gives like your little cousin in the pool, like trying to be a waterbender and like moving around the wave and going whoosh and like sending the electrons over, and then like knocking a bug out of the pool. That's the vibe of this to me. It's not luxury. But you push down, you move the double bond over, kick off the leaving group, and then that is how you get over to your enone. The technical name for this mechanism is the E1CB. E, because it's elimination, we made a double bond. 1, because the rate limiting step is unimolecular, it doesn't require a second molecule. And CB from conjugate base. This is the conjugate base of our aldol. So, she's fancy. But for this, I think it just takes a minute to get in you and to like internalize it and try writing it out. So I want you to try out challenge problem 7 here, and I only want you to do the first step so far. So the first step, we see that we don't see. We have a dicarbonyl, and then we have this aldehyde here. What do you think is going to be the more acidic one, the dicarbonyl or single carbonyl? Dicarbonyl, exactly. So we know that this is going to be our nucleophile. We're going to make an enolate over here. And then this is going to be our electrophile that we're attacking. We attack an aldehyde, so it's the aldol reaction. So I want you to do an aldol condensation. So get all the way to the enone version. I'm going to give you a few minutes to write that out. This is challenge problem 7. And actually, just as a guide, I'm going to put up the curved arrows over here so you can see the mechanism and be trying to copy that onto this new molecule. So I'll give you a few minutes. How'd you do? Bad. So if you went and deprotonated this and pushed it down, that's totally fine because these are going to be equal on both sides. They're both ketones. So either way it could work. I'm not taking pictures of every question. I'm going to post the annotated one today and it's going to have everything. I'll post it now. Yes. Again, I feel bad after the exam, so I'm like, let's do the whole...
Is that
You said, you fear. You fear. Wow. So we haven't done anything with it yet. So we're about to finish it off. So we've only done step 1 of the reaction here. Yeah. So getting to this enone at the end, are we together there and then we're going to do the end together?
Yeah.
Yeah, totally.
Why did you attach like the alkene instead of attaching the double bond O? I mean, sorry, with the negative charge in the O. And like the first.
Like, why did we push down?
No, I understand why you pushed down.
Mhm.
Why did you like do the nucleophilic attack with the alkene instead of using the negative charge? Yeah.
Like, why did we not do this?
Yeah.
Because that's not the polarity of it. Like, forming the double bond again is going to be really thermodynamically favored because that double bond is a more stable product. So even though it looks like we have an O minus here, remember it's delocalized via resonance on all 3 of those. So anytime you have an enolate, the O is not going to do anything other than maybe grab a hydrogen and become an enol. Also, I can't believe I just put in a caramel right before I'm about to talk. It's going to be like this. So it's always going to push down and then have this attack.
So it's always going to be the alkene.
Yes, and that's why we say the alpha carbon is going to be the nucleophilic site. Yeah.
Also, so where we have the alpha carbon hydrogen and this alpha hydrogen, right, that is removed in the first step, and then when you're, after you form the addition product, is it always going to be the same? It's the same, like,
Like, these arrows are the aldol mechanism, yeah. So the hard part is just determining, like, which molecule is nucleophile electrophile, which side we make the aldol on. Because also, like, hypothetically, you could make an enolate with one of these alpha hydrogens, right? But the thing is, you have to know it's far more acidic between the 2 carbonyls. Yeah, so that's where the tricks are. So let's talk about this second step, the NABH3CN. In the instructions of the problem, they say this is a variant of NABH4 that will only add 1,4 to enones. So we saw a version of this early on in the course that will only add 1,2. What's the version that will only add 1,2? All the way back in lecture 3. So what do we sprinkle in? Yes, so we sprinkle in CeCl3 to NABH4 to only add 1,2. That's the Lusch reduction. So now there's a 1,4 only way as well. And again, you're not responsible for this for like a test or something, but just like the more you know. So what we do is it's the same exact mechanism as NABH4, but we would just write out our boron hydrogen bond. It's going to attack 1,4 only. We push in, push up, do our conjugate addition. And the last step, we just do an alpha protonation as part of our conjugate addition. And that will get us to our product here. Yeah?
So what if we use an OET base first rather than an OH? Or if there's something...
No, it's just used as a base. Yeah.
So it doesn't matter. So I can use OH or OET
Yep.
interchangeably.
Yeah, and this problem just gives you OET. So, yeah. And then for the next one, this is challenge problem 2A. So in challenge problem 2A, we get a weird thing. So we have a Grignard interacting with a ketone, which normally we'd expect it to add the phenyl group and turn the carbonyl to alcohol. We do not see that. Instead, we see a free benzene. Where did this free benzene come from? Yeah, the phenyl group. And then, oh boy, oh buddy buster. If this is our R, 1, 2, 3, we have 2 of these. So we have like 2 equivalents of this, which I'll make that skinnier. So 2 of this molecule interacted with each other. Our Grignard didn't attack. What's going on? So if we are going from this MgBr to this benzene, normal benzene would have a hydrogen there. So what does this MgBr Grignard need to grab? It needs to just grab a hydrogen. So is it acting as a nucleophile or a base? A base. And oh my gosh, isn't that the theme of the summer? Grignards are bases. We see it so often. Happens to the best of us. And so what we do is we make this enolate, and then we know it's going to interact with another equivalent of our starting molecule over here. So we're going to push down, and this is going to attack, do our classic kind of aldol attack. And then what we get, I'll kind of label these. So I'll call the alpha carbon that attacked blue star, and then the one that was attacked, the green star. And then we get a little stuck. So with this, O minus at this point in the aldol reaction would go and grab a hydrogen from the solvent. But do we have any hydrogens in our solvent if we're using a Grignard? No. So this is weird. We then have to leave the base step. We have to go on to step 2, the acid workup, in order to continue. So now we grab an H+. We are in step number 2. And now this is the tricky part of this question. We are now in acid. So all of the rest of the steps of our aldol condensation now, we need to do the acid version of them. So normally at this point, what we would do is have a base come and grab this hydrogen, but we don't have bases, so we're in acid. What do you think we should do? Protonate something, yes. So in this case, we still need to eventually remove this hydrogen. So what we are going to do next, and I'm just going to kind of give you a sketch of it, we would protonate our carbonyl, and then water would come and go and deprotonate here. And then we can do the super lone pair push. So again, it's going to be a little bit different than the one that you just did because now we need to be in acid conditions. Another thing, so if we are in acid, can we kick off an OH minus? No. So we have to kick off H2O instead. So just warning for like different protonation states. But the same game plan for the mechanism. Yeah.
I have a question. So, how would we have known that the Grignard here is acting as a base and not
Just based on the products.
just based on the product?
Yeah, like if we had asked you to predict this, you would predict it attacks the carbonyl. And honestly, that's going to happen a good deal of the time. These are probably side reactions, but this is the one that we want you to explain in this question. Yeah. And so I am going to keep on chugging, sorry, because we're a little bit behind. I want to make sure we get through everything. So I'm going to do my quick transition. Big idea number 4. So the exact identities of our starting materials result in different variations of this. So our classic aldol is when one molecule that we have turns into an enolate and it attacks another equivalent of the same molecule. That's what we saw in the problem that we were just working. That was a classic aldol. And this is something that I don't feel like is commented on in enough organic chemistry textbooks. With this family of reactions, there's actually a really strong concordance to the cha-cha slide. So, again, I really hope it's adopted by more texts in the future, but until then, I will carry the torch. So our classic aldol, of course, in the cha-cha slide is going to be
Slide to the left.
slide to the right. Same one, sliding to the left, sliding to the right. One's a nucleophile, one's an electrophile. Does anyone want to guess what the crossed aldol is going to be?
Crisscross. Crisscross.
And that's where one enolate attacks a different ketone or aldehyde as the electrophile. So that's our crossed aldol. And then intramolecular, if they are on the same molecule, this one is fun. This is going to be, it does a little wiggle and like attacks with itself. It could also be, again, two of them work. And then the other big thing about these reactions is that they are reversible. So we can do the aldol reaction going forward, and we can do it going in reverse. I know, yeah, you got there. Take it back now, y'all. Where we can bust open our enone, or we can bust open an aldol and take it back to 2-carbonyls as the starting material. So again, I strongly advocate for the cha-cha slide concordance of this family. Can we end it off with a cha-cha slide of the, where is it? There's a secret box.
Freeze! Everybody clap your hands.
Woo, the aldol reaction, so much fun! Ah, cowabunga! We're really trying. So, the retroaldol, I'm not going to go through beat for beat with y'all, but I have a nice like figure up here, but it is literally undoing the aldol reaction. So our last step of the aldol, we kicked off an OH. First step, OH adds. Then before that, we made an enolate. So now we have to unmake an enolate. We have to protonate at the alpha position. So it's really doing it exactly backwards. Any of these reactions that you're doing on the P side or for practice, I think it would be good practice to also try to do it backwards, just to make sure that you have internalized these and can bust it out either way on the exam. So the other thing that's going to be really, really helpful with these reactions from lecture 10 are being able to do disconnections. So step 1, we have to be able to spot an aldol product, and that's where we need our new functional groups, so our aldol and our enone. Now, our enone, what we would do is we would circle here, and we would label our alpha and beta position. We know that enolate chemistry makes a bond between the alpha and a beta, and so if we're going to disconnect it, we are going to cut in between that alpha and beta position. So when we do that, with enolates, we know that the alpha carbon is the nucleophile, right? It's an enolate nucleophile. So on the alpha side over here, I'm going to make that side into an enolate. And on the beta side, we know that the electrophile for the aldol reaction is a carbonyl. And then this enolate we could even take back further to be, what's the starting material before we make the enolate, the starting carbonyl? And what do you notice about these two? They're the same. So this is our classic aldol. So can you try to do a disconnection in the second and third one? So you're looking for those beta hydroxycarbonyls, the aldols, and enones. And so spot them, identify alpha beta, cut along the alpha beta bond, and then turn the alpha side into the enolate, turn the beta side into the carbonyl.
Sorry, did you say that the enolate was the nucleophile? Or the-
Yeah, the enolates are nucleophiles. Also, does anyone want these flashcards? Treehead Extra. They're very aesthetic. Salmon.
I already took a stat, but if no one wants it.
You said, I'll go in for seconds.
I mean, I'll wait until we have someone to
Heard. So for this middle one, we saw we had an aldol here. We identified alpha beta, cut between it. On the alpha side, we turned that into an enolate. On the beta side, carbonyl. And here there was a hydrogen already present, and so that becomes an aldehyde. Then we can take our enolate back even further and see what the full starting molecule is. Now, what functional group do we have in the product? The third one. Like, do we have an enone here? Not an enone because that's an sp3 carbon in the middle. Do we have an aldol here? No, because this is alpha hydroxy, not beta hydroxy. So what do we have? We have a trick question. I'm so sorry. Silly, goofy, trick question. But again, it's really emphasizing that the part of the challenge of lecture 10 is spotting the reaction, spotting the reaction that's happened, and being able to look at a molecule and be like, certainly wasn't aldol. That was not one of the things that happened here. That's a skill that we want you to be confident in. And so be watching out for this. We'll do another practice later. Be on the lookout. Yeah.
So the reason you said that that one couldn't work is because, like, well, part of the reason is that the top one was an sp3 carbon. So the only way that would work is, like, if the last one, it had an alcohol next to it. Is that...
Wait, when you say the last, like,
So,
you
like,
mean
the one
this?
next to it, yeah.
Yes, yeah. So, like, here, if this was moved over, like, 1 over here or something, then that would be at the beta position, beta hydroxy. Yeah. Or if we had this double bond moved over 1, that's an alpha beta unsaturation. It's all about that alpha beta position. So if we just have it at the alpha, it doesn't help us, you know? Sorry for the trick question. Last one, challenge problem 3A. Let's talk through a little bit of this. So we're not going to do the full thing with this, but scan the starting materials and products. Do you see any of our new functional groups? Yeah, we have an enone. And then what about the starting material?
No.
Alpha, beta, beta hydroxy. Again, spotting these aldols. It's a new skill to work on, essentially. So, okay, going from an aldol to an enone, that seems like we're just going from the aldol addition to aldol condensation. But what we would expect to happen if we did that is we would expect to just turn this into a double bond and kick off the OH. And that's clearly not what happened here, right? We have a whole different ring. So if we are kind of at this point right here, the aldol addition product, and we know going further is not going to give us the correct product, the only thing that we can do is go backwards. So let's do a disconnection here. And then see if we did like the retro aldol going in reverse. Let's cut along this bond and see what it looked like before. So on that alpha side, that's where we have our enolate. And on the beta side, that's where we have our carbonyl. And let's go back even further. Let's go and protonate this. And get it to a straight chain. So this is a 1, 2, 3, 4, 5, 6, 7 carbon chain with 2 ketones on the end. 1, 2, 3, 4, 5, 6, 7. And so we can get to this straight chain here. And this enolate that we had formed was the inner enolate. It is, if we deprotonated at either of these carbons I've highlighted in green, we would go this direction and get that enolate. But is there another enolate that we could form? We could do this outer enolate. So let's say we go and deprotonate this. Then this enolate could push in and attack the other side, and now we form a 1, 2, 3, 4, 5, 6-membered ring. And now all we have to do is the aldol condensation mechanism. So like on the actual P set, you will need to show the retroaldol and the aldol steps here. But do you see how this disconnection and getting back to this intermediate was really, really helpful to have a like segue point or a like safe harbor to land here. And we know that we can do the straight up retro aldol arrows to get here. And then we can do straight up aldol arrows to get here. This reaction I think is really a beautiful one. It's great for like exams because it's making you think backwards and forward about these aldol reactions. And to me, this is giving, I don't know if anyone knows Dance Dance Revolution, but the Rasputin, like the Rasputin, he does this little move where he's like up, down, up. This is like, I'm in one ring. Oh, I'm a straight chain. I'm another ring. It's like, there's kind of a playful vibe to it, or there's a menacing vibe. You decide. I like to call it playful. But with that, I am going to keep on chugging just because there is a lot, and I want to make sure that we can get through as much as we can. So, when we were talking about the aldol, what was our electrophile? What functional group in the aldol reaction was our electrophile? Aldehydes are ketones. So can we do a column response of like aldol, electrophile, aldehyde, and ketone? 1, 2, ready, go. Aldol, electrophile, aldehyde, or ketone. Aldol, electrophile. Aldol, electrophile. Great. The new idea is the Claisen electrophile is an ester. So our new big idea is enolates can attack esters. So Claisen electrophile, ester. Claisen electrophile, ester. Claisen electrophile. Ester. Beautiful. And I know that it seems kind of silly, but like if you can't clock what the electrophile is, you will do the wrong mechanism. And so it's really one of the core like fundamental ideas here of who you attack in lecture 10 determines what reaction you are doing. So here we have our enolate, we have an ester, and what we form as our product is a beta dicarbonyl, also called a 1,3 dicarbonyl. So we have 2 carbonyls separated by 1 carbon in the middle. And the reason why we get this product comes from everything looks the same and normal here. We form our enolate, the enolate attacks the carbonyl, but then at this intermediate, when we attack an ester, we now have a good leaving group on this molecule. So we can reform a carbonyl here and kick off the OR. And again, to do it like a really direct comparison with aldol, in aldol, this is just a carbon group. So you're not going to be able to kick anything off. And that's why in aldol, this will just go grab a hydrogen and become an alcohol, and then we'll try to kick it off another way. Here it can reform a carbonyl, so it will. Also clock that if we are kicking off this OR, then in our product, our electrophile side could never be an ester, right? Like if we had this, we have an ester here and a ketone here. This is the product of a Claisen reaction. If we tried to ask which one of these carbons, our carbonyls, was our electrophile, well, our electrophile has got to be the one without an OR group in the product, because in the Claisen reaction, you kick off that OR group. So since this one still has an OR group, this must have been our nucleophile side. Because like once our nucleophile, like we make our enolate, once it reforms, we're done with her. Like, so if we had an OR on the other side, it gets to stay. That the electrophile OR has to leave. Now, you do this, you say, beautiful, I'm done. I have my beta dicarbonyl. Points, please. I'm so sorry. Dicarbonyls, are they more or less acidic than normal carbonyls? More acidic. So if you had a base that was strong enough to deprotonate a single, like alpha hydrogen, then it's certainly going to deprotonate the dicarbonyl alpha hydrogen. And so what you have to do, and it's really annoying, I can't stress that enough, is you have to deprotonate it and push up, and then you do an acid workup step where you immediately undo it. It's tedious and boring. And also, if you don't do it, that's minus 3 points on the exam. I dislike it. It's kind of like the horror movie It Follows, where it like the scary thing like follows very slowly, but also if it gets you, it's gonna get you. Like this isn't hard, but also if you forget it, you will lose 3 points. And when I took organic chemistry 2, like almost a decade ago at this point, do you know what I forgot to do on the exam? I forgot to do the annoying step. Am I still bitter about those 3 points?
Yes.
Yes, I am. Thank you. Thank you. Yeah.
But why do we have to do that? Like, what did you
Because we are still in base. Like when we do this, the whole time we are in base. And so since we're still in base, we are going to deprotonate an acidic hydrogen.
Okay, so I just have to remember if I still have that base there, I have to use it no matter what.
If you are in, like, acidic things are formed. But I'm going to set you all up for a practice and I can answer some more questions. So I want you to try this skill builder on page 4B of just drawing out the Claisen reaction. So here, you're going to make one side of this an enolate and then have it attack the ester on the other side and do just the classic Claisen. So I'll give you a couple minutes for that. Okay, so how'd you do on the Claisen?
I think there's a third arrow in the first step.
Oh yeah, thank you. Oh my gosh, so forgetful. Everything good? Yeah.
Wait, what if I just I did it the other way? Like I used that Esther group on like
Yeah, that's totally fine. It's symmetric, so it should work. Any other issues with this? Minus 3 points on the exam. It can happen that easy. It follows. I hate it. So what we have to do is be like, I formed my product. No, you didn't. No, you didn't. And you have to deprotonate it. Should we push up to the ketone or the ester? We should push up to the ketone because the ester already has a lot of electrons around it. So we want to go to the one that's more electron poor. And then immediately undo it. And like, this is the thing. You should feel disdainful for having to write this. I am. And so I tag it appropriately. Every time I do this, I write annoying. It really, I hate it. I hate it.
I have to remember always do your annoying step every single time.
For the Claisen, yeah. Anytime you have a dicarbonyl in your own base, it's going to get deprotonated. And then for this next one, we are not going to fully work through it, but this 3B is just like the Rasputin one for 3A. So you are going to do a retro Claisen. You're going to get to a straight chain. And then you are going to do a different Claisen. So I'll let you try that on your own with the practice, but this is the idea of it's in one version of the Claisen, it's going to go to its straight chain, and then do another version of the Claisen.
What's it say?
A different Claisen, yeah. Okay. So the Claisen has its own diaspora, just like the aldol, where you have the classic, the cross, the intramolecular, the retro. The only thing I'm going to point out about this is you can have a cross Claisen where an ester enolate attacks a different ester electrophile, but your enolate doesn't have to be an ester. Your enolate could have come from a ketone or aldehyde. The thing that makes it a Claisen reaction is the electrophile being an ester. So again, the identity of the electrophile for everything in lecture 10 determines what the reaction is. So, if the electrophile is a ketone aldehyde, what reaction is it? Thank you. If the electrophile is an ester, what reaction is it? Claisen. Ding dong. Let's try this retro Claisen like disconnection here. So what we do is we spot our beta dicarbonyl that told us that Claisen has happened. And here, essentially there are two ways that we could count this. We could call this alpha, this beta, or we could kind of consider this green one our home base, and we call this alpha, this beta. So let's draw the two different ways we could disconnect it. So if we had the blue one as our home base, our alpha beta bond that we're going to disconnect is here. On the alpha side, we're going to make our enolate. And our beta side, since it was a Claisen, we need what? An ester. So pick your favorite OR group. I'm just going to do OME. So that's one way of doing it. But if we consider the green star one over here to be our home base, then if we cut between its alpha beta, what we have is our enolate is now on the right because that's our alpha side in the green version. And the beta side over here is the electrophile. Now, is there a difference between the two of these here? No. So either one works. You can disconnect it. But over here, in this middle one, we still have a beta dicarbonyl, but one side is an ester. If it is an ester in the product, was this the nucleophile side or the electrophile side?
No, nucleophile because it would have gotten kicked off.
So The ester side is our nucleophile side because if it was the electrophile, its OMe group would have been kicked off. Do you buy that? Or is it still confusing?
Maybe that one more time.
Yes. So, your electrophile, let's start off with this electrophile over here. In the course of the Claisen reaction, its OMe group gets kicked off. And so in the product, the electrophile is going to be the one that's not an ester. Yes, when we start off, the electrophile is an ester. But in the product, it's no longer an ester because we've kicked off the leaving group. So if we're seeing this over here, we know that this top part has to be the electrophile since it no longer has its OR group. And we know this bottom part had to be the nucleophile. So what we do is we consider this the home base, alpha and beta, and we cut here. So for this, what we would get is our enolate looking like this. And on the beta position, we need to make it into the ester that's being attacked. So again, that's a weird nuance that yes, the electrophile being an ester is what makes it Claisen, but then after the reaction happens, she's no longer an ester. Work. Do we have a Claisen happening in this third one? We're looking for a beta dicarbonyls. Are there any beta dicarbonyls? Are you sure? This is alpha dicarbonyls.
Oh wait, bottom right.
This is alpha, beta, gamma dicarbonyls.
The O and OH.
And that's an alpha hydroxy.
The other one.
That's a aldol. Do we have any Claisens? Did any Claisens happen? Oh, silly goofy. It's a trick question.
I don't appreciate these very much.
Hey, would you rather be tricked now or during the final exam?
Would there be a
We're not intentionally trying to trick you on the final exam for the mechanisms, but we will give you it, and you will have to understand, based on the molecule, what reaction happened, a Claisen or an aldol. And so if you're not scanning for that, you could just try the wrong one, not like thinking it through. And so that's why I like do this here, to make it feel a little frustrated now, so that you don't feel big frustrated later. Ding dong. Okay, I'm gonna keep on chugging. Oh, not her. I want you to take 30 seconds, and I want you to try to predict what is going to be the product from doing a aldol reaction between these two, or which of these are not going to form. So take 30 seconds. Told you the sound cues are going to go off today. Okay, so do any contestants want to buzz in? Jeopardy style, tell me which do you think are formed? What is B? Any other answers? What is E? This is the Daily Double, come on, what's the answer? What is all of them? Every single one of these could be formed because for this red and orange one, you could form the enolate on the left, and then that could attack the red-orange one, or it could attack the green-blue one. You could form the enolate on the right and attack the orange-red or the green-blue. And then the same thing for the green-blue. You have 4 different enolates and 2 different electrophiles after that, so you are going to get all 8 of these options. So obviously, this is not something that we want if we are going to try to do like synthesis or control these reactions, which you're not going to be doing like synthesis things with this for the most part. If you did see it in a box problem or a synthesis, it would be the easiest version where we have like set things up so it's not tricky. Like we do not want this to be primarily a line reaction synthesis. We want it to be primarily mechanisms. So how do we control the chaos? We can limit the different possibilities by using symmetry, lack of alpha hydrogens, ring size, and sequential addition. So symmetry, if we use a symmetric molecule, then we just only have one option for our enolate. And so that cuts it down by half, like our number of possibilities. Another thing that we could do is use one-sidedness. So if we have one side where there isn't an alpha hydrogen, because there's not an alpha carbon, or because like it is has 4 bonds to other things, then that side can't be an enolate. Like over here, even this aldehyde one, that's not an alpha hydrogen, because it's not an alpha carbon, it's on the carbon of the carbonyl. So each of these only have the option for one enolate to be formed. Similarly, if we want to ensure something is an electrophile, we make it impossible for it to form an enolate. So we make it have these one-sided things, or sorry, these no alpha hydrogens on both sides, in which case it can only be an electrophile. It can't be our enolate nucleophile. Then for ring size, this is kind of what we saw with the Rasputin. So if the option is, we can either use one of these interior enolates, and with this we would make a 1, 2, 3, 4, 5, 6-membered ring, or we can use one of the exterior enolates, in which case we would make a 1, 2, 3, 4, 5, 6, 7, 8-membered ring. Which do you think is more stable, a 6-membered ring or an 8-membered ring? Actually, it's 6. Once rings start to get above 6, then it starts kind of folding in weird ways that it can kind of bump into each other, like diaxial strain, or like the A value stuff. And so typically we're going to favor forming 5 or 6-membered rings. And then the last one, we don't really do much in our class, but especially if you're studying for the MCAT, you might see this reagent come up, so I just wanted to clock it. This is called LDA, which is a really common base for enolate chemistry. Lithium diisopropyl amide. Basically, it's a nitrogen with a negative charge, so it's really basic. And what we can do is we can add LDA, and then we'll convert all of our starting material into an enolate. And then our thing that we want to be the electrophile, we could add dropwise in. And when we are doing it that way, this never gets the chance to be turned into an enolate, because right when it gets added to the reaction mixture with this enolate, it's going to be attacked and do the reaction that we want it to do. So we are never going to ask you to do this on like exams or anything. It's more of an FYI. Some courses, like classes that spend 2 or 3 weeks on enolate chemistry, will get into this and all the details, but a little bit much for us. And with that, we transition to our last section. The last section of the last section. Our final big idea. Enolates can do other things. Essentially, we talked about enolates attacking ketones aldehydes, the aldol reaction, enolates attacking esters, the Claisen reaction, but enolates can attack more functional groups. So if we have an enolate attacking an enone, this does the Michael addition. So all it is literally just doing conjugate addition on the enone. So this is a really great integration of like lecture 3 stuff. Then once we add it and get to our final product, the thing that we have that's kind of interesting is we have a 1,5 dicarbonyl. And that comes from this like enone, this like how far the carbons will be spaced out. You'll always get a 1,5 dicarbonyl. And typically our enolate nucleophile, so our electrophile is the enone here, the nucleophile that we use for the Michael addition is typically going to be a dicarbonyl. And so we will have a dicarbonyl here, and this is the new bond that we made between the end of our enone. This one also, watch out, because we have dicarbonyls, this one will have the annoying step. Because even after we do this, we will form this, but we'll still be in base before an acid workup, and so we'd have to deprotonate it. So technically, I think that should be 1, this, 2, H plus workup. So, doing conjugate addition. Enolates can also just straight up do SN2. So we're in like lecture 6 land, where we push down and we do a backside attack on alkyl halide, and suddenly we've added an alkyl group. Nothing too crazy there. Then, in like kind of lecture 5 stuff, this beta dicarbonyl is the product of a Claisen. And we could do an ester hydrolysis, turn it into a carboxylic acid. And if we heat that with this beta dicarbonyl and the carboxylic acid, it's going to do this cool little intramolecular reaction where it produces a CO2. It makes this like 6-membered ring transition state, which makes it a lot more likely for the reaction to happen than even some other intramolecular reactions. So this is one that's really favorable and very predictable. But if you ever have like gotten rid of a carbonyl or gotten rid of a carbon, the decarboxylation is a really, really great and kind of powerful tool for that. The last thing is the Monic reaction, which is more of a reaction scheme than a straight up like curved Taylor mechanism. So in the Monic reaction, we take an amine and we take an aldehyde, and lecture 5 style, we make an iminium. So once we have our iminium, then the other thing in our beaker is a ketone, which gets turned into an enol. Why is it an enol instead of an enolate? Well, remember we're doing this in pH around 5, so very slightly acidic conditions. So we're not going to have a strong base. So we're going to have to do our acid version of the tautomerization. But then once you have these guys, the enol and the iminium, the enol is a nucleophile and the iminium is an electrophile, kind of like what you saw on the Strucker. And this is going to give you a beta aminocarbonyl. So kind of like a beta hydroxy for an aldol, beta aminocarbonyl is for the Monic. Now the Monic is a really great final exam question because it does lecture 5 stuff, it does lecture 10 stuff, and also it's kind of tricky to see a Monic reaction and the like exact details of it. So I would high key expect one of these on the final exam, and I believe that there are some in the practice finals as well. But let's try this one from challenge problem 6 just to kind of spot some things. So we're looking for an aldehyde, an amine, and then a like ketone or like enol. Which of these do you see on the molecule? Yeah, aldehyde and amine, great. So let's go ahead. We know that these are going to come together, and I'm not going to do the full mechanism, but the amine formation from lecture 5, sorry. So we formed an iminium, but then we need an enol, and I don't see another carbonyl at all, or an enol. Like I don't see any oxygens. So in that case, do we have anything that can act like an enol, or maybe we can use the products to help us? So in the product, where does it look like we've made a bond? Yeah, like we need to connect this pentagon with this pentagon. And so this is our new bond. Okay, well we know this is an electrophile. Is this carbon nucleophilic? Is this something kind of like an enol? Who is she? Enamine. So she can push down and go and attack at the alpha carbon. And then that will lead us, after one more step, to our final product. The last thing I'll leave you off with for this lecture is just this second reminder that the really important thing for being able to answer lecture 10 questions on the exam is being able to just clock which reaction you're talking about, which is going to involve these new functional groups, these ones that are a little bit larger in compound functional groups. And so just knowing that you can't think about these in isolation as an alcohol and a ketone, you have to be thinking about aldols and enones and 1,5-dicarbonyls and all of that. That is going to be how you don't get tripped up on these. But without further ado, thank you for coming to the last section. It's been really fun working with you all. And again, you're almost done. You've learned so much. Oh, that's really unfortunate. I'm so sorry. But just again, think about how much information you've learned in the past 6 weeks. It's crazy. It's crazy. Yeah. But have a good weekend. The other big thing, please get rest this weekend, because I know that y'all like push yourself for this exam too. PSET 6 is going to be much shorter. We've done a lot of the hard, like heavy lifting of the PSET, so please get some rest, take care of yourself, and then we'll finish out strong next week. But have a good weekend. Yes.